Bismillahirrahmanirrahim. Assalamu alaikum, students. Today I'm going to start a new course. I will name this course as, let me write the course title. Mathematics in the physical sciences. Right? This is the course name. Mathematics in the physical sciences. I hope this course would be helpful and useful for all undergraduate students studying physics, chemistry, and engineering. When I was studying physics at college level and at university level, I was myself not comfortable with mathematics being used in physical sciences, that is in my subject, because of the reason that normally we encounter teachers in physics who are not very good at the mathematics being used in the subject. So I hope all of you will enjoy it, learning, and I will enjoy it teaching. So let me start this course. I will divide this course into chapters, and the chapter 1 of this course is infinite series. Power series. So this infinite series, power series, is our first chapter. So let us start the first topic in this chapter. So my first topic in the first chapter is the geometric series. We are going to consider the geometric series as a simple example of many of the ideas involved in series, right? So we will use geometric series to understand those ideas which are involved in studying series. Let me refresh your memory. a geometric progression, let me write it this way, in a geometric progression we multiply each term by some fixed number to get the next term, right? I repeat, in a geometric progression, we multiply each term by some fixed number to get the next term. For example, 2, 4, 8, 16, 32, then 64, so on. Similarly, 1, 2 by 3, 4 by 9, then 8 by 27, then 16 by 81. Similarly, in general, we write A, AR, then AR square, then ARQ, so on. Let me name them. This be A, this B, and this C. Now, all of these progressions are examples of geometric progressions, right? Let me check it. 2, 4, 8, 16, 32, 64, 1, 2 by 3rd, 4 by 9, 8 by 27, 16 by 81. Then in general, we write A, AR, AR square, ARQ. Now, the fixed number which we have defined is in general written as R, and the first term of the progression is represented by A. So this is here my first term. Or first entry in the progression, then it becomes first term when we talk of series. And this R is a fixed number. So you can see in general form of the geometric progression, which is written in C, we multiply first term by first term by R, we get the second term AR. Then we multiply R to second term, to get the third term, that's AR squared. We multiply third term with R, we get the fourth term AR cubed. In the first case, that is the first example, example A, that fixed number is 2. So you see your first term is 2, then you multiply 2 with 2, you get the second term 4. You multiply with fixed number 2 with the second term, that is 4, you get 8. You multiply 8 with 2, you get 16. You multiply 16 with 2, you get 32, and so on. And in the example B, that fixed number is 2 by 3. You multiply 2 by 3 with 1, you get the second term 2 by 3. You multiply second term with 2 by 3, you get a third one, that is 4 by 9. Then you multiply 2 by 3 to 4 by 9, you get 8 by 27, and then on you get 16 by 81, and so on. So all these A, B, C are examples of geometric progressions. It's clear? In a geometric progression, we multiply each term by some fixed number to get the next term, as we have given examples A, B, and C, right? Now it is easy to think of examples of such progressions, right? Suppose the number of bacteria in a culture doubles every hour. Then the terms of A represent the number by which the bacteria population has been multiplied after 1 hour, 2 hours, and so on. I'm saying, suppose the number of bacteria in a culture doubles every hour, right? Then the terms of 1, that is A, first geometric progression, represent the number by which the bacteria population has been multiplied after 1 hour, 2 hour, then 3 hour, and so on. You can see if it doubles everywhere, then the first entry is the number after first hour, because it will be twice the number started with, that is 1. After 1 hour it will be 2. After 2 hours it will be double, that is 4. After 3 hours it will be double, that is 8, and so on. This A will represent this population of bacteria in a culture after 1 hour, 2 hour, and so on, assuming that the bacteria population doubles every hour. right? So we can think of such examples. Or suppose a bouncing ball rises each time. Let me write it in some other color. Or suppose a bouncing ball rises each time to two-thirds of the height of the previous bounce. Then the second geometric progression, B, would represent the heights of the successive bounces in meters if the ball is originally dropped from a height of 1 meter. Let me repeat it. Suppose a bouncing ball rises each time to two-thirds of the height of the previous bounce, then B would represent the heights of the successive bounces in meters if the ball is originally dropped from a height of 1 meter. You can see first its height was 1 meter, then after one bounce its height will be two-thirds, then after one bounce its height will be one more bounce, its height will be two-thirds of the first, two-thirds of the second one, it will be 4/9 and so on. So this geometric progression represented by B will represent then the heights of the successive bounces, right? So you can see how we can think of the examples involving these geometric progressions, right? Now, in our first example, it is clear that the bacteria population would increase without limit as time went on. I repeat, the first example, that is the population of bacteria would increase without limit as time went on. You can see it is going up, increasing, and so on. After every 1 hour, it is doubling. After 64, then it will be double 64, then it will be double of that. So this population would increase without limit. right? Assuming that nothing like lack of food prevented the assumed doubling of bacteria each hour, right? In the second example, however, the height of bounce of the ball decreases with successive bounces, and we might ask for the total distance the ball goes. I repeat, in the second example, the height of the bounce of the ball decreases with successive bounces. As you can see, first it is 1, then it's 2 by 3, then it's 4 by 9. So it is decreasing with time as the ball moves. The height of the bounce is decreasing with successive bounces. So we can ask for the total distance the ball goes. The ball falls a distance 1 meter, rises a distance 2 by 3 meter, and falls a distance 2 by 3 meter, rises a distance 4 by 9 meter, and falls a distance 4 by 9 meter, and so on. Thus, it seems reasonable to write the following expression. Let me write it. It seems reasonable to write the following expression for the total distance the ball goes. 1 plus 2 times 2 by 3 plus 2 times 4 by 9 plus 2 times 8 by 27 plus so on, which can be written as 1 plus 2 times 2 by 3 plus 4 by 9 plus 8 by 27 plus so on. Let me name it as equation 1, or let me write it as D, where the 3 dots mean that the terms continue as they have started, each one being 2 by 3 the preceding one, that is 2/3 the preceding one, and there is never a last term. Understand it? By writing this expression for the total distance the ball goes. As I said, first the height was 1 meter, then it bounces to 2/3 of the previous one. So it rises 2/3, then it will fall 2/3. Then it will rise 4 by 9, it will fall 2 by 9. So excluding first one, all heights are attained twice, because ball first rises 2 by 3rd, then falls 2 by 3rd. It started with falling through 1 meter. That's why in the sum there is no 2 times in the first term. It is 1, then in each entry 2 is multiplied. because it falls and rises. Those distances 2 by 3, 4 by 9, 8 by 27, it falls as well as rises. In the first term, it only falls through 1 meter. Then we took this 2 as common and we write it 1 plus 2 times 2 by 3 plus 4 by 9 plus 8 by 27 and so on. And these 3 dots here, we said they mean that the terms continue as they have started, each one being 2/3 of the preceding one, and there is never a last term. Now, let us consider the expression in the parenthesis in equation D. So let us write, let us consider the expression in parenthesis in D. That is this equation which we wrote for the total distance the ball goes, namely 2 by 3 plus 4 by 9 plus 8 by 27 plus, let me name it as equation E, right? Now this expression is an example of an infinite series. This expression is an example of an infinite series. Right? And we are asked to find its sum. Because if we want to know the total distance the ball goes, we have to evaluate this series in the parenthesis. So we're asked to find its sum. Now you need to understand that not all infinite series have sums. Let me write it. Not all infinite series have sums, right? You can see that the series formed by adding the terms of equation A, which represented the population of bacteria 2, 4, 8, 16, 32, 64. This series, if you form the series by adding the entries in equation A, that series does not have a finite sum, right? It is visible because the entries are becoming bigger and bigger as we move in the progression. So if you add 2 plus 4 plus 8 plus 16 plus 32 and make a series, that series is also infinite series, and that series does not have a finite sum, right? However, even when an infinite series does have a finite sum, we cannot find it by adding the terms, because no matter how many we add, there are always more. Thus, we must find another method. I repeat what I said. I said this expression is example of an infinite series. Then I said not all infinite series have sums. Then I told you that it is visible, you can understand it, that if we form the infinite series using the entries in the progression A that does not have a finite sum, right? And even when an infinite series does have a finite sum, we cannot find it by adding the terms, because no matter how many we add, there are always more. Thus, we must find another method, right? What is the method? Let us first find the sum of n terms in this E. So let us find the sum of n terms in E. That is this infinite series, right? The formula for the sum, the formula for the sum of n terms of the geometric progression C is, by C I mean the general form of this geometric series, which we have represented by C. The sum for the n terms, the formula is Sn is equal to A times 1 minus r raised by n over 1 minus r. We name it F. So what is the sum of formula for sum of n terms of the geometric progression C? It is Sn is equal to A times 1 minus r raised by n over 1 minus r. So using F in E, we use this formula F to find the sum of n terms of infinite series E, right? So let us do it. We find what we find. Let me use, okay, I will use the same page. Use another color. Sn which is first term is our 2 by 3. Then we have 4 by 9. Then we have so on. Now nth term will be 2 by 3 raised by n, right? 2 by 3 raised by n. So let us use this formula. What we get, Sn is equal to 2 by 3 times 1 minus 2 by 3 raised by n over 1 minus 2 by 3. 2 by 3 times 1 minus 2 by 3 raised by n over 1 minus 2 by 3. Check it. 2 by 3 is A. It is the first term. R is that fixed number, which we can see is 2 by 3. That's 2 by 3 times 1 minus 2 by 3 raised by n, right? Then downstairs it is 1 minus r, where r is 2 by 3. So it is 2 by 3 times 1 minus 2 by 3 raised by n over 1 minus 2 by 3. So what it turns out to be is 2 times 1 minus 2 by 3 raised by n. Check it. At home and convince yourself. It is 2 times 1 minus 2 by 3 raised by n. Let me name it as G. It's my Sn. So I name it equation G. This was E, then it was F, so it is G. You can see as n increases, 2 by 3 raised by n decreases and approaches 0. I say as n increases, 2 by 3 raised by n decreases because 2 by 3 is less than 1 and it approaches 0. Then the sum of n terms approaches 2. Because when 2 by 3 decreases as n increases and it approaches 0, this Sn, which is the sum of n terms, approaches 2 as n increases. And we say that the sum of series is 2. What we say that the sum of the series is 2, right? This is really a definition. What is the definition? The sum of an infinite series is the limit of the sum of n terms as n tends to infinity. Let me write it. The sum of an infinite series is the limit of the sum of n terms as n approaches infinity, right? Then from equation D, then from D, this is our D, right? When this sum is 2, then we can find the distance the ball goes. What is that? So then from D, the total distance traveled by the ball is 1 plus 2 times 2, which is 5, right? Because 1 plus 2 times, now this sum is 2, this 2 times 2, so the total distance traveled is 5, right? So this is an answer to this mathematical problem, right? Now series such as D form a geometric progression whose terms form a geometric progression. Let me show you this series, which we name a D. Was a D it was this one E. This is our series. So let me write now the definition. Use another color. Series such as E, that is this infinite series, right? Whose terms form a geometric progression are called geometric series, right? We can write a geometric series in the form A plus AR plus AR square plus so on plus A R raised power and minus 1 plus so on, right? Let me name it as first, right? Now this sum of the geometric series if it has one is by definition written as limit n tending to infinity Sn. We name it second. Right? Where Sn is the sum of n terms of the series. Right? Now, one more important point here is a geometric series has a sum if and only if mod r is less than 1, and in this case the sum is a over 1 minus r, a over 1 minus r. Let me name it third. Right? The series let me write it separately. The series is then called convergent. Right? So this is all for today. Let me summarize the lecture. In the start, I introduced the course, title of the course, and its usefulness. Then I said that the first chapter is infinite series, power series. Then we started with geometric series. First, we talked about the geometric progression. I said in the geometric progression, we multiply each term by some fixed number to get the next term. Then we give the examples A, B, C. C is the general form, and A, B are two examples. In the first example A, the fixed number was 2. R is 2. In the case of second one, that is B, the fixed number was 2 by 3. A was the first term. In the first example A, it was 2. In the B, it was 1. Right? Then we talked of examples of geometric series. We talked of number of bacteria in a culture. If it doubles every hour, then the terms of A would represent the number by which bacteria population has been multiplied after 1 hour, 2 hour, and so on. Then we talked of a bouncing ball which rises. If it rises to two-thirds of the height of the previous bounce, then B would represent the heights of the successive bounces in meters if the ball is originally dropped from a height of 1 meter, right? Then we said that uh, if we talk of the total distance the ball goes, we can write this expression for it. Then this parenthesis is example of an infinite series. And we said all infinite series do not have sums. And we said if we form an infinite series by adding the entries in the first geometric progression A, which represented the population of the bacteria, it does not have a finite sum. And we said even when infinite series has a finite sum, we cannot add it by just adding the numbers, by adding the terms, because no matter how many we add, there are always more terms. So we must find another method. Then we took the example of the sum of n terms, and we wrote the formula for geometric progression, and we used that, and we found this sum as 2 times 1 minus 2 by 3 raised power n. And we said if n increases, 2 by 3 raised power n decrease and approaches 0, and we gave the definition of the sum of an infinite series. We said the sum of an infinite series is the limit of the sum of n terms as n tends to infinity. And accordingly, we solved for the distance the ball travels, which turns out to be 5 meters. And we said that the geometric series, we give the definition of geometric series, and we wrote its general form, and we said it is sum of the geometric series is by definition the sum of its n terms as n tends to infinity, which is written by second. And we said a geometric series has a sum if and only if its modulus of the fixed number r is less than 1, and in that case it is simply as a by 1 minus r. A is the first term in the series, r is the fixed number, and when it has a sum, the series is called convergent. So this is all for today. I hope you will enjoy this course as the course proceeds. Don't forget to like, share, and subscribe my channel. You can give comment in the comment box. Thank you. God bless you. Assalamu alaikum.